Okay, so with new operations comes new properties. And what I'm about to do is make a list of some standard properties that are possessed by coordinate vector operations, or addition, subtraction, and scalar multiplication, the ones we just defined, right? And you can see if I slide down here, you can see there's 10. There's going to be room for 10 properties, and this is where the list is going to go. Now, with the understanding that coordinate vectors can be expressed as row matrices or column matrices as well, some of these certainly won't be a surprise, especially when you consider how similar the definitions were for vector arithmetic that we just did and the matrix arithmetic that we defined in Chapter 1. So this theorem is going to consist of our list. So here's what we're going to start with to work with. We're going to have three vectors, and you can see I've used the letters u, v, and w to represent them, and they're all going to be in Rn. So they're all going to be coordinate vectors in some n-dimensional space for some positive counting number n, and we've got two scalars k and m as well. So here's the properties. We'll start with the commutative property of vector addition, and this is going to look very much like one of the properties of matrix addition. So if you take u and v and you add them, and they have to be of the same dimensions for the addition to be compatible, and if all u, v, and w all are in Rn, they have the same number of coordinates, then we're free to go ahead and add these. But we could also write v plus u, and we're going to get the same thing. And really, it boils down to the fact that if you take two real numbers and add them up in either order, you get the same thing. So if you apply that to the level of each individual coordinate, what you end up getting is this property, which is referred to as the commutative property of vector addition. And there's also an associative property of vector addition, just like there were with matrices. So if I want to add up all three vectors, u, v, and w, well, addition is a binary operation in the sense that it's designed to be applied to two objects. So if you want to add up three objects, you have to pick which ones, at least in principle, you have to pick which ones are going to add up first. So if I wanted to add u and v, and then calculate the result, which is now, once I perform that addition, the result is going to be a single vector that I can add to the vector w. It turns out I could have also done the following. I could also take the vector u and add that to the result of the calculation of adding v to w. So I could add v and w together, calculate the result, and then add that result to u, and it turns out that I will get the same thing. So this is called the associative property of vector addition. Okay, the next property they'll say, and this one again will probably be no surprise if you consider that the analogous property for real numbers. If I take the vector u and I add it to the zero vector, and by the way, the zero vector in this context, the only thing that would make sense here, if we were to treat the zero vector as a vector in Rn, a coordinate vector in Rn, we'd have to say what its coordinates are. So let's just clarify that over here. The zero vector in Rn is just the vector with n coordinates, all of which are equal to 0. If I could write it as a column matrix, and then it would be an n by 1 matrix where every entry is equal to 0. If I wrote it as a row matrix, it would be a 1 by n matrix, again with every entry equal to 0. But if I write it as a coordinate vector as I have here, then that's how I can represent the zero vector. So this is, in Rn, is the zero vector. Okay, we did actually define the zero vector already, but that was in the specific case of being a geometric vector in R2 or R3. But you can also have a zero vector, you can have in any dimensional space, you can write the zero vector as a coordinate vector in Rn for any positive counting number n. So if you want the zero vector in R3 as a coordinate vector, it's just the vector with three coordinates, 0, 0, and 0. If you want the coordinate vector in R4, that's the zero vector, you just take all four coordinates to be 0. So in any event, that's what the zero vector is. So with that in mind, let's finish this property. If I take any vector u and I add the zero vector to it, well, remember, vector addition just works coordinate-wise. So the result would just be calculated by taking each coordinate of u and adding the corresponding coordinate of the zero vector, which would just be 0. So you'd be adding 0 to every single coordinate of u, and the result is going to be Well, just the same as what you started with. If you add 0 to each coordinate, you're not going to change any of them. So the result is just going to be the vector u again. If you add the vector u to the vector negative u, well, what's going to happen? What does negative u mean? Well, if you remember from the previous page, if you put a negative sign in front of a vector, what you're really doing is you're multiplying that vector by the scalar -1. What that really just amounts to multiplying every coordinate of the vector u by the scalar -1. So really what you're going to get here is you're going to get a vector which consists of n coordinates, and each of those coordinates are going to be the negative of the corresponding coordinate from u. Well, when you add those two vectors together, you're going to add each respective coordinate. And you're going to get a whole bunch of negatives just canceling each other out. And the result is going to be 0 for every single coordinate. So what you're going to end up getting is the 0 vector. It's kind of like with real numbers. If you add 3 and -3, you get the number 0 when you add those together. Well, it just turns out, due to the way vector addition is defined, the same thing happens when you do it with vectors. If you add a vector to its negative, you end up getting the 0 vector. Okay, the next property says that scalar multiplication distributes into vector addition. And what that looks like as a property is if I take k and I multiply it by the sum of u plus v, it turns out that I'll get the same thing if I calculate the scalar product ku and the scalar product kv and then add the results. So it turns out if I do either of those calculations, I get the same thing. And it really just boils down to the distributive property of real numbers. Now for property 6, it tells us that if we take a scalar product of m times the vector u, so remember we got two scalars, and right back at the beginning we have two scalars to work with, k and m. So if I take this vector u, which is up here, and I multiply it by the scalar m, well, the result is going to be another vector. And the result is really just going to have each of the coordinates of u are going to get multiplied by m. Now if I multiply the entire result by the scalar k, it turns out I'll get the exact same thing as if I were to just first multiply the two scalars together, k and m, and then the result will be a scalar, right? K and m, if they're both scalars, you multiply them together, the result is a scalar, and I can take that scalar and multiply it onto the vector u. And it may or may not be a surprise, but you're going to end up getting the same thing in both cases. Okay, so that's property 6. Property 7 says that scalar multiplication distributes into, well, in property 5 we said that scalar multiplication distributes into vector addition, but it turns out that scalar multiplication is also going to distribute into scalar addition. And here's what I mean by that. If you take k and m, your two scalars, and you add them together, well, the result is going to be a scalar, which you could then multiply onto the vector u. Well, what you can also do is you can multiply each of those two scalars k and m onto u individually, and the result in both cases is going to be a vector. So you can add those two vectors together. Oops, pardon me, you're going to get, let me just start this one over. Yeah, you can add those two results together. So if I multiply the scalar k by u, I'll get ku, and if I multiply the scalar m by u, I'll get mu. And it turns out if I calculate those two scalar products individually and then add them together, this is vector addition here, then I'll get the exact same thing as if I were to add the two scalars first and then take the resulting scalar and multiply it onto the vector u. Property 7 says both of those will be the same thing. I messed this one up here a bit. Unfortunately, I hate doing that, but that happened. Okay, so property 8, this one I think is really not a surprise, but if you take the scalar 1 and you multiply it onto the vector u, what do you think you're going to get? The temptation is probably just to guess that you're going to get u, and it's a good guess, and in fact it's correct, but let's look at why. Why is that the case? Let's try to think it through. What is u? U is a coordinate vector, right? It has a whole bunch of coordinates, and what does it mean to take a scalar and multiply it onto a coordinate vector? Well, it has the effect of just taking every one of the coordinates of this vector and multiplying it by this scalar, which is a 1. So if you take each of the coordinates of u and multiply them by 1, then none of them are going to change. And the result is going to be exactly what you had in the first place, which was u. So that's why that happens. So watch out for that. If you find that you're just guessing that the property is going to look a certain way just based on what you know about real numbers, just watch out that you're not making any leaps. It's good to think about these properties in terms of what they mean. And each one of these properties, by the way, can be checked carefully and verified. They're not just true because I said so. You can actually check them carefully, and some of that will appear in the exercise sets. Property 9, this is going to be another one that's probably one that you'll guess. If I take the scalar 0, because 0 is a scalar, and I multiply it by the vector v, could have used u here, but we have 3 vectors at the top, u, v, and w, so might as well use a different one for this property. If I take the vector v and multiply it by the scalar u, what am I going to get? And a good guess that probably many of you will guess is going to be 0. And what I've written is actually not quite correct if I want to be picky. So it's true in some sense that if you take 0 and multiply the vector v, any vector v by that scalar 0, you're going to get 0. And if someone asked you, well, why is that the case? You might be tempted to answer with, well, anything times 0 is just 0, right? Which, that's true, but there's a context that goes with that. When you grew up in elementary school, probably and high school, you grew up with the idea that just anything multiplied by 0 is just 0. And while that's certainly true, that is a property of real numbers. And we're not working with real numbers right now. We're working with scalar multiplication of scalars and vectors. So is it still true that if you multiply a vector by the scalar 0, you're just going to get 0 again? And the answer is yes, but you're not going to get the scalar 0. Think about what's happening. Okay, ignore the right-hand side here because we're going to change this. If I just look over here and I've got the vector v, which has a whole bunch of coordinates, and I multiply each of those coordinates by the scalar 0, the result for each one of those calculations is going to be 0. So what I get over here is not just going to be the scalar 0. What I'm going to get is an n-dimensional vector, each of which's coordinates are going to be 0. So really, you're going to get this, which is the 0 vector, not the scalar 0. So when you take any vector and you multiply it by the scalar 0, the result is the 0 vector. So not the scalar 0. So watch out for that. And then lastly, if I take any scalar at all and I multiply it by the 0 vector, well, what am I going to get? 0 again, right? If I multiply the scalar k by 0, I'm going to get 0 in some sense. But be careful. This is a scalar product of a scalar multiplying onto a vector. The result ought to be a vector as well. And if you guessed the 0 vector as the result, that's exactly correct. So that's the last property, the 10th property. So if you multiply the 0 vector by any scalar, the result is still the 0 vector. Okay, so let's move on from these properties. By the way, where are you going to use these? You'll use these on the exercise sets. There's lots of vector calculations that you're asked to do, and some of them can be sped up significantly if you carefully use these properties rather than working them all out from scratch. So I'll leave that to you to explore a bit, but keep these properties in mind when you do the exercise sets, because they can save you some time. But be careful that you're not, if you're using properties to take shortcuts, make sure they are these properties, because if you're using some other property that's not contained in this list, it could be the case that you're using a fake property or one doesn't actually hold, and you could run into trouble and get an incorrect result that way. So be careful. These are your properties that you can use, and I would be very, very hesitant to use anything that's not in this list. And in other words, check it carefully, whether that be working it out by hand and checking it from scratch, or speak with me. Okay, so the last idea on this page that we'll talk about is the idea of parallel vectors. Lines can be parallel, right? We have an idea for what it means for two lines to be parallel. It means they don't intersect. And we can also talk about what it means for two vectors to be parallel. And I should clarify, two lines are parallel exactly when they don't intersect. That holds as long as the two lines are known to be distinct. But in the case of two lines that are actually the same line, just different representations of the same line, those are technically included as being parallel as well. So I should be careful. But in any event, that kind of is a little bit of a distraction from the main point here. But the idea is we can talk about when lines are parallel, so we can also talk about when vectors are parallel. So what's the intuitive definition, which is given right here. So two vectors are parallel if they have the same direction or the opposite direction. And why would they be allowed to have the opposite direction? Well, think about this example back here on the second page. These two vectors have opposite directions of each other, but there's nothing stopping them from being parallel. In fact, if you were to look, it might be hard to tell because this one's so short, but if you move this line closer to this one, you'd see that they are actually parallel, even though this one's pointing in the opposite direction, right? So, but those are the only two candidates, right? Vectors that are they have the same direction, identical direction, or the exact opposite direction is the only way two vectors can be parallel. But we can actually quantify that mathematically. And well, really, and the way to do that is really embodied in this example, because what was the point of this example, right? This was just how to write down scalar multiples of a geometric vector. And they were, in other words, they were all multiples of that same original vector. So all three of these vectors are parallel to V, and hence to each other as well. But what is it that makes these three vectors parallel to V? Well, the fact that they're all multiples of V. They're scalar multiples of V, right? This one is 2 times V. This one's negative a half times V. And I probably should have had brackets around there. This one is this one is 3 times V. They're all scalar multiples of this original vector V, and that's really what makes them parallel to V, right? And hence to each other as well. But that's where this definition comes from on this page. So we're going to formulate the idea of parallel vectors mathematically with this definition. So two vectors, coordinate vectors, we're dealing with coordinate vectors now, x and y, that are in the same dimensional space, right? They're parallel if there exists a scalar value k such that one of these two equations holds. Either k is equal to k times y, and this would just mean that x is a scalar multiple of y, or y is equal to k times x, and this would just mean that y is a scalar multiple of x. It could be either or. If either of these two equations holds for some value of k, well then we say that the two coordinate vectors x and y are parallel. Okay, so that's the definition of parallel vectors.